Solution concentration. So if you take a glass of water and you put some table salt into it and stir it up, the salt seems to disappear, right? You can't see it anymore. What's actually happening is that the salt is dissolving in the water and you're forming a homogeneous mixture. The salt is still there. If you taste the water, you can tell it's still there. That's something you can try at home. If you put that water in a pot and boil all the water away, be careful at the end, you'll see that the salt is still there. So they just mixed. So a homogeneous mixture like this is also called a solution. And there are two parts to a solution, the solvent and the solute. How we define what the solvent is can vary a little bit, but in general the solvent is whatever part of the mixture there's more of. So if you sprinkle a teaspoon of salt into a cup of water, there's a lot more water than salt. And so the water is the solvent. Often the solvent is a liquid, but it doesn't have to be. Another thing about the solvent is the solvent keeps its state. So in our example here, water was a liquid. The solution is a liquid. The solute is whatever part of the mixture is present in lesser amount. The solute may or may not change state. So the salt was a solid. When we put it with the water and mix it up, now the solution is a liquid. So the solute has changed its state from solid to being dissolved in the liquid. And you can have more than one solute. Typo. Come on. What? Oh, seriously messed up. So solutions are mixtures, and because they're mixtures, the composition can vary. You can have a little bit of solute or a lot of solute. Pure substances have constant composition. Like water, pure water is a compound, a pure substance, and it's always got the same ratio of hydrogen to oxygen. But in solutions, it can vary. So we need to indicate something about how much of each component is present when we describe solutions accurately. And we often call this a concentration. We don't need this with pure substances because we just use their chemical name and that gives us all the information we need. But if I tell you, oh, this is a glass of salt water, that tells you nothing about how much salt is in a given amount of water. So we need to have concentration units. And we also have some qualitative descriptions. These are not attached to numbers, and they are relative terms. So a dilute solution has a relatively small amount of solute compared to the amount of solvent. A concentrated solution has a larger amount. And there's no hard line distinction between what's dilute and what's concentrated. They're just relative. So we can see here there's a lot more of the little blue circles, and here there's fewer. This is dilute and this is concentrated. Now we'll get to the numbers. So a common way to express solution concentration that chemists use a lot is molarity. Molarity, and the abbreviation is a capital M. It's important that that be a capital M because a lowercase m by itself is a meter, and we don't want to get those confused. Molarity is defined as the amount of solute in moles divided by the volume of the entire solution in liters. So the units end up being moles per liter, or capital M. Here's an illustration showing how we might make a solution that has a particular molarity. And you are going to be doing this in lab this afternoon, so pay attention to this. So when you're making it from a solid, you're going to weigh out the required amount of solid. Here we're trying to make a 1 molar sodium chloride solution. 1 molar means 1 mole of sodium chloride in 1 liter of solution. So you figure out how much sodium chloride by mass you need. You do a molar mass conversion there. So 1 mole of sodium chloride would be 58.44 grams of sodium chloride. And you measure that on the balance. And then you put that into a flask that will hold the correct amount of liquid. Here we want a liter of solution, and so we're going to use a 1 liter flask. Then you're going to add some water. You don't want to fill it all the way up at first. You want to just fill it partially. I wouldn't even necessarily go that high. I'd maybe fill it up to about here. And then you're going to want to swirl it around. You need to get this solid to dissolve. Once you get this filled up into this neck, it becomes very difficult to mix. And so we want to get it dissolved before we get it filling it up into the neck. So once it's all dissolved, then you're going to add your solvent, here it's water, until the bottom of the meniscus is at the line. There should be either an etched line or a printed line on the neck of the volumetric flask. The way these things are made, they're blown glass, and so the exact size of this bulbous part of the flask is going to vary a little bit, but we have this long neck, and so after the glassware is made, it's calibrated by putting this line in just the right place. So if you compare a bunch of flasks, you'll see that that line might be higher or lower in different flasks. But if you fill it to the line, it's going to give you 1 liter. Okay? These flasks are designed to contain the amount specified. They're called volumetric flasks, and they're one of the more precise pieces of glassware that we have. Once you get it to the line here, and you probably don't want to do that last little bit even with a wash bottle, because at the end you may need to add 1 drop of water. So a good way to do that at the end is put some DI water in a small clean beaker and use your pasteur pipette, your transfer pipette, that plastic one in your drawer. It's like an eyedropper, and then you can just add 1 drop at a time and get the bottom of the meniscus right at the line. If you go above the line, you're kind of sunk. You really should start over. It kind of depends on how precise, how accurate your concentration needs to be. But you can't just suck some out and say that that's perfect, because there will be some solute in this water. So you don't want to overfill this. Then you put the stopper on. You put your hand around the neck of the flask, and you put your thumb over the stopper so it doesn't come out. And then you have to invert the flask and wait for the air bubble to go all the way up, and then tip it right side up again, and you should do that like 20 times to make sure that it's thoroughly mixed. And then you have your 1 molar sodium chloride solution. Any questions?
But if the salt stick to your finger?
The salt won't stick to your finger because you're going to put a stopper here. You're going to put a stopper here, and you're going to use your thumb to hold the stopper. Yeah, you could use your thumb to seal it, but then you're going to get chemicals on your thumb, right? So we don't want to do that. We're going to use a stopper. Any questions? Well, let's do a calculation of solution concentration. Calculate the molarity of a solution made by adding 45.4 grams of sodium nitrate to a flask and dissolving it with water to create a total volume of 2.50 liters. So we need to remember what the definition of molarity is. So molarity is moles of solute divided by liters of solution. And it has to be moles and liters. You can't use grams and milliliters or something else. Then it's not molarity. Molarity is always moles per liter. Okay, so what's our solute in this solution? The sodium nitrate. So that's our solute. What's the solvent? Water. Water's the solvent. Okay, so do we know how many moles of solute we have? No, we're going to have to calculate that. Do we know how many liters of solution? Yeah, they gave that to us. 2.50 liters. What happens a lot is that they give you the volume in milliliters, because we tend to use smaller quantities in chemistry, and then you have to convert it to liters. But here, we're just given liters. So that other piece of information we have is a mass, 45.4 grams of sodium nitrate, but we need moles of sodium nitrate. Can we convert grams to moles? Sure we can. And we can do that in one step. So grams of sodium nitrate to moles of sodium nitrate, and then we'll divide by the sodium nitrate. And where do we get the number for that conversion factor? It's the molar mass. So we're going to need to look at the periodic table and calculate that. So sodium is 22.99. It's one of those. And nitrogen is 14.01. There's one of those. And then we've got 3 oxygens. I thought I was doing that down a little lower. Okay, so we get the calculator, 22.99 plus 14.01 plus 3 times 16. 85. How many sig figs does that number have? Well, 85 only has 2, but how many should it have?
4.
Should have 4. So 0.00 grams per mole. So, you know, sometimes you have to add some significant digit zeros in there. 85.00 grams per 1 mole of that. So we've got 45.4 divided by 85. And this is equal to 0.534. This result here only has 3 sig figs because our starting mass had 3. So there's 3. This is not a final answer. I want to write down 2 extra digits so that I don't get any rounding errors. And so that's my moles of sodium nitrate. I'm going to take that number and put it into my equation. 0.53412 moles. I've underlined the 4 just to keep track of sig figs. It's easier that way. Here I've got 3 sig figs on top and 3 on the bottom. So my molarity should have 3 sig figs. Take that result and divide by 2.5. 0.213. There's my 3 sig figs. Write down 2 more. The units are moles per liter. And when I round that, I'm going to get 0.214 moles per liter. Another way to write that is 0.214, come on, capital M. Any questions? One way to make sure that your capital M is understood to be a capital M is to underline it. It's a thing that we do. Because if I draw an M like this, is that a capital M or a lowercase m? Which is it? Lowercase? No, it isn't. It's capital. Right? No matter what you say, I'm going to make it wrong. So relative size is tricky to judge, right? So we want to be very clear. We don't want to be confused and think that it was 0.214 meters. Any questions? Yes?
Can you use that underlining thing for any letters that are similar?
That's a good question. Yeah, we don't use the underlining thingy for other capitals. I'm not sure why. But we do, like, you can't write with an eraser. Did you know that? It doesn't make a mark. So Z's and 2's sometimes look alike. So I tend to cross my Z's. And then 7's. 7's can get mixed up with several different things. I tend to cross my 7's also, and cross 7's. So those things help, but yeah, I don't know of any other underlining things. Any other questions? So molarity, having units of moles per liter, can be a great conversion factor. So we use this as a conversion factor between the moles of solute and liters of solution. A 0.500 molar sodium chloride solution, that means 0.500 moles of sodium chloride per liter of solution. Or we can write that upside down. So we can go from liters of solution to moles of sodium chloride, or from moles of sodium chloride to liters of solution. Then you combine that with a molar mass, and you can do all kinds of stuff. How many grams of sucrose, giving you the formula, because there's no way we expect you to know that. How many grams of sucrose are in 1.55 liters of 0.758 molar sucrose solution? So we read the problem, we write down the numbers. So we've got 1.55 liters, and we've got 0.758 capital M. Capital M, as the abbreviation for the unit, gets used a lot because it's so easy to type. But students tend to forget what it means. So instead of writing this down, I would encourage you to write the full thing down. 0.758 moles divided by liters. Because these units are a fraction. And if you use the capital M, you may go, I don't see how to put these things together. So that's what we're given. What are we asked for? Grams of sucrose. So C12, H22, O11. The next question is, we've got two numbers. One of them is where we start our conversion. This is a dimensional analysis problem. Do we start with the liters or the moles per liter? Liters. This is a simple unit. It's just a single unit liter that cannot be used as a conversion factor. This one, moles per liter, that's going to be our conversion factor. So we need to go from liters to something. Well, these units are a clue. We have a relationship between moles and liters. So it's liters to moles. That's moles of solute. Can we go from moles of the solute to grams? Yeah, all we need is the molar mass. So we've got 1.55 liters and two conversion factors. We're going to have moles over liters, moles of sucrose. And then we're going to have another one with grams of sucrose per mole of sucrose. Try that again. 11. We do that so the units cancel out. So this factor was given to us. This is a conversion factor that applies only to this particular problem. It's not universally true, but it's true here. So 0.758 moles. The 0.758 goes with the unit mole. Per liter, if you want a number down there, it's per 1 liter. Then we need the molar mass of sucrose. 12 times the mass of carbon plus 22 times the mass of hydrogen plus 11 times the mass of oxygen. Sucrose is the substance in table sugar. That's all table sugar is sucrose. $342.296. The units on that are grams per mole. So that's our number that we're going to put in for this last term, 342.296. grams per mole. So we've got 1.55 times 0.758 times 342.296. How many sig figs will the answer have? 3. My volume had 3, my molarity has 3. Molarity is not an exact number. So, and this had 4, and so I should have 3 here. I'm going to write down my 3, 402, and then I'm going to put down 2 more, just because, and the unit is grams. So then when we round this for our final answer, 402 grams of sucrose. Any questions? Solution, dilution. Sounds like the title of a bad poem. We are going to do some things with dilution today in lab. Solutions are often stored as concentrated solutions. We call them stock solutions. We keep them in the stock room. They are in stock. And so if we want a concentration that's lower than that, instead of getting out the bottle of the solid substance and weighing it and all of that, we just use the more concentrated solution and we dilute it. This is a lot like buying concentrated frozen orange juice. It comes in the can, you bring it home, it's a lot easier to transport than a big gallon of orange juice, and it keeps longer in the freezer too. You come home and you dump the concentrate into a pitcher and then you add water to it. You dilute it. So it's the same idea here. When I'm making orange juice, so I take the can and I dump all the orange goodness into the pitcher, and then as I add water, am I changing the amount of orange goodness in the pitcher? No, I'm not changing the amount of orange stuff. I'm just changing the volume. I'm changing its concentration, but all the orange stuff that was there to start with is still there. So when we dilute a solution, the amount of solute doesn't change, the volume of solution changes. And what that ends up meaning is that the moles of solute in your starting solution is equal to the moles of solute in your second solution. The moles of solute don't change. So because of that relationship, we get this equation here. The molarity of the first solution times the volume of the first solution is equal to the molarity of the second solution times the volume of the second solution. Or M1V1 equals M2V2. That's an important equation. You should remember that one. The concentrations and volumes of the stock and diluted solutions are inversely proportional, if that means anything to you. So this is the equation we're going to use. How do you dilute a solution? We're going to do this today too. Well, first of all, you need to figure out how much of the concentrated solution do you need, and then what your total volume of your dilute solution would be. And so that would be done using a calculation like this. So the volume of the concentrated solution, 10 moles per liter, 0.15 liters of that is equal to our diluted solution, 0.35 moles per liter, times its volume. As the volume increases, the concentration decreases. That's what inversely proportional means. And so we end up with 1.5 moles of solute in each solution. But this solution is larger in volume and lower in concentration. So we measure out 0.15 liters of our more concentrated solution. We put it into a volumetric flask. Then we're going to add water. I would add water, up to here, mix it as best I can, and then continue adding water again till the bottom of the meniscus is right at that line. Then you stopper the flask. You hold it with your thumb over the stopper, because it's really a bummer when you turn the flask over upside down and the stopper opens, falls out, and your solution goes all over the floor. You've made a mess, you've potentially endangered yourself, and you have to start over. No good. Put your thumb on the stopper. Mix it 20 times. Any questions? let's do a practice calculation. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.750 calcium chloride solution? So a key word here is dilute. That should say, we need the dilution equation. The dilution equation, M1V1, it's a V, believe me, equals M2V2. There are other ways to solve this, but this is the method that seems to be most understandable for most students. So that's the equation we need. There are 3 numbers in the question. We should write those down and identify what they mean. So here I've got 100.0 milliliters, and I've got 5.00 moles per liter, and I've got 0.750 moles per liter. It doesn't matter if solution 1 is concentrated or solution 2 is concentrated. It just matters that you get the volume with the correct molarity. So this is saying 100 milliliters of this. Those 2 numbers go together, they're referring to the same solution. So this is a volume and this is a molarity. Since it came up first, let's call it number 1. So I'm going to label these. This equals volume 1, and this equals molarity 1. So this one is the other solution. This must be number 2. This is a molarity, so I'm going to label that molarity 2. And what are they asking me to find?
The volume of solution 2.
Volume of solution 2. So we are looking for volume of solution 2. And they specify the units in milliliters. So now what we want to do is we want to take this equation and rearrange it. We are going to solve for V2. Should be pretty simple because there's no fractions in here, and that's what really messes a lot of people up. I didn't do a very good job of spacing this out. That's better. Do you like that? I can move it. So let's rearrange this. We're trying to get, thank you. Oh, I thought, you close the door. This stupid train. I had quite the conversation with it yesterday. We want to get V2 by itself. So that means I need to divide by M2 on this side so the M2s cancel out, and I need to do the same thing on the other side. So now I have V2 is equal to molarity 1, volume 1, divided by molarity 2. Everybody okay with that? I'm going to plug my numbers in. So the volume 2 that I'm looking for is molarity 1. So I have that listed. That's 5.00 moles over liters. Write those as vertical fractions, please. Volume 1 is 100.0 milliliters. And then I'm going to divide this by the other molarity, 0.750 moles per liter. Check the units. This milliliter doesn't cancel liter here, but that may or may not be a problem. In this one, it isn't a problem, because moles per liter in the numerator cancel moles per liter in the denominator. So this cancels that. And the unit that's left is milliliter, which happens to be the one I want. So I've got 5 times 100 divided by 0.75. 666.66666. How many sig figs should I report on that?
4.
3, 4, 3. 3. This one has 3, 5.00. This has 4. Sometimes students will see this 100.0 and then they'll write 100, which technically has 1 sig fig, so be careful. And then this one has 3. So we should do this with 3 sig figs, and this equals 667 milliliters. One of the reasons that we care about sig figs is it can actually save you time in the lab. I mean, your calculator shows you this. That's really precise looking, right? Is it necessary to get that exactly precise with that volume? No, it's not going to do anybody any good because these other amounts are more approximate than this is. And so by paying attention to sig figs, we know, oh, well, we just need to get it to the nearest milliliter. We can use a big graduated cylinder, that'll be fine. We don't have to get out anything fancy. Any questions? Solution stoichiometry. So we're going to come up on some variations on our grams to moles to moles to grams thing. Molarity relates moles of solute to liters of solution, so it can be very useful in looking at an amount of reactant or product that's in a volume of solution. If we know its concentration, we don't have to go to grams and then to moles. We can go from the volume directly to the moles. So this is a variation where instead of starting with a mass and using molar mass to get to moles, we're going to start with a volume and use the molarity to get to moles. And we can get to moles of the other using the mole ratio from the balanced chemical equation. And then we can use the concentration to get to the volume of substance B. So here's an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation. This reads more complicated than the mass-to-mass stoichiometry calculations. But it's actually easier because we don't have to calculate much of anything. We don't have to calculate molar masses. So I'm going to read through the problem again, picking out the numbers, using my equation to organize them. So 0.150 molar nitric acid. Okay, so I'm going to write that under the formula for nitric acid. 0.150 moles per liter. Write it as a vertical fraction. And then I'm given a volume of sodium carbonate. So 35.7 milliliters of the sodium carbonate. And then I'm given the molarity of that solution, moles per liter. And what is the question? Volume of nitric acid, question mark, in milliliters. So I'm given a volume, and I'm asked to find a volume. So this is volume to moles to moles to volume, instead of grams to moles to moles to grams. It's a variation on a theme. So I'm going to start out with my given. This is what I've been given, 35.7 milliliters of that sodium carbonate. And then I'm going to go to moles of sodium carbonate. Oops, I need a line there. And then I'm going to go to moles of nitric acid. And then I'm going to go to milliliters of nitric acid. So down here I'm going to have moles of sodium carbonate. And down here I'm going to have moles of HNO3. And over here I would have milliliters of sodium carbonate. So the moles are canceling just fine. But I've got a little bit of trouble with liters. This will cancel, but this concentration is moles per liter, not moles per milliliter. So what I've got down here is really moles per liter. And this concentration is moles per liter. So I need to have liters here instead of milliliters. You see why I did that? This is my molarity. It's units of moles per liter. It doesn't have milliliters in it. So is this going to be a problem? Do we have to convert milliliters to liters before we get into this part? You can. Just like, do you remember the kilograms to grams to moles to moles to grams to kilograms problem from Monday? This is the same idea. You can convert the milliliters to liters and then go moles per liter, moles to moles, liters per mole, and then convert back to milliliters. That'll work just fine. It just is very tedious to me. So what I'm going to do is the same thing I did with the kilogram. I'm going to treat the milli, which means 10 to the minus 3, as a separate thing, and I'm not going to cancel that out. So liters of sodium carbonate cancel with liters of sodium carbonate. Milli is left here, and here I've got liters, and so at the end I can put those two together and get milliliters. So this is the molarity of the nitric acid, 0.150 moles. So that needs to go down here on the bottom. And the molarity of the sodium carbonate is 0.108. It's moles per liter, so that number goes on the top. And then this number, the numbers here come from the coefficients. There's an understood 1 in front of sodium carbonate and a 2 in front of nitric acid. So my calculator is showing me 51.408 milliliters. How many sig figs should that have? 3. So 51.4 milliliters of nitric acid. Any questions? If doing it that way didn't make sense to you, please come talk to me during lab and I can show you other ways to do it.